Hello and welcome to the STEMCstudio channel and another video in the Geometric Algebra first course series. In this video we are going to carry on the mini-series that we established with the position and attitude video, and we're going to move on to the kinematics of our rigid body motion. So that is what we're going to do is we're going to try and move our body based upon the velocity it has, and we're going to try and rotate it based upon its angular velocity. The video will be in two parts. There's a fair amount of theory in the first part. I'm going to work through that theory, and I don't think you'll have any trouble if you've been kind of like following the Geometric Algebra first course and building the multivector and understanding how geometric algebra works. So that's going to be an important prerequisite. So that's a warning. Okay, so let's get started. And what we'll do is we'll do the theory first, and then we'll implement it in code. So here is where we'll start. Recall that so far we have a very abstract rigid body with a bunch of points on it, and all that we can do right now is we can just position it in space. But what we'd like to learn how to do is how to connect the position and attitude, that is the rotation angle, if you like, of this body with its angular velocity and velocity. So let's do that in two parts. I am going to stop the code, and we're just going to focus on the theory. So the first thing we're going to do is we're going to try and update the position of the body, and that's the body.x property. Strictly speaking, big X is actually what we call the center of mass of the body, and we'll see that a little bit more later. I'm hoping that you're familiar with that, and this is more or less just a conversion course to geometric algebra. But if that's not the case, I hope there's enough information for you in this video for you to understand what's happening. Okay, so we start with a definition of the average velocity, and the average velocity, which is a vector, is just the difference of the final position from the initial position and divided by the change in time. Okay, so nothing amazing about that. We can define also this little time interval, and we tend to do that because when we run simulations, we will step forward by a certain amount of time. Quite often that time interval is constant, but sometimes it will vary. And so just by rearranging this equation above, you get this x final, the position at the end of the time interval is equal to the position at the beginning of the time interval plus the average velocity multiplied by the time interval. Okay, but there's a problem here. If we're updating x final, we need to know the average velocity, but the average velocity depends on x final. So how do we get out of that? Well, the way we're going to do it is we're going to say, look, if the interval is small enough, then the average velocity over the time interval is going to be very much like the initial velocity. And so we can say to a good approximation that the final position is equal to the initial position plus the initial velocity times time. And as long as delta t is small enough, and by small enough I mean just small enough for this to be a good approximation, we won't get into it any further than that, then this is a good way to proceed. Okay, so this is our updating rule for the position of the body. And in terms of the code, it would look something like this. We would have body.x equals body.x plus velocity times time. And we can do this calculation because we have operator overloading. So this should be completely understood by your code in STEMCstudio. Okay, so this is not a math equation, this is not an equality, this is an assignment of the thing on the right-hand side, updating the thing on the left-hand side. Okay. All right, now there's a little problem as well, is that we don't really want to keep track of the velocity of the body. Instead, we'd rather keep track of the momentum, because the momentum will connect us more easily to ideas about acceleration and forces. Okay, forces being the rate of change of momentum. So Instead, we're going to have the momentum on the body, and we need a way to convert the momentum into a velocity. Now, that's kind of quite simple to do. You've probably seen this relationship before. It's the non-relativistic, or low speed, if you like, low speed compared to the speed of light, approximation for how do you convert a momentum into a velocity. And you have to know the mass of the body, and essentially that allows you to compute the velocity as being momentum divided by the mass, or you can just say that this equation says that the momentum is equal to the mass times the velocity. Okay, so putting that all together in code, we would expect to see something like this. We store the momentum of the body on the body, and we store its mass too. And whenever we need the velocity, we just calculate that. So we say the velocity is just the momentum divided by the mass. The momentum, of course, is going to be a vector in our geometric number, and the mass is going to be a scalar in our geometric number. So we can divide the two to get the velocity. And then the updating rule then is just the updating rule we had before. We say the body's position is the original position of the body. This is the initial position, plus velocity times time. And obviously we're in code, so we have to put the explicit multiplication symbol in there. Okay, so let us try to implement the motion, the translational motion of the body by using a scheme something similar to this. We're going to add momentum, the momentum property and the mass property to the body. And then somewhere we're going to compute the velocity, and we're going to update the position in this fashion. Okay, so the first thing we have to do is go to our rigid body, and we're going to add the momentum property. So I'm going to put it in here right next to the position property, because they sort of go together in a sort of way. And what would be a good initial value? Well, I would say 0 probably makes sense, because we don't want the thing sort of flying off when we first create it. So we'll do that. So this will be the linear momentum. And in addition, we're going to need the mass. So we're going to use big M is the total mass of all of the different little mass points in our object, assuming it's discrete or just summed up or integrated if it's not. So here's geometric. What would be a good value for the mass? Well, we don't want to get a division by 0 when we divide the momentum by the mass. So I think a good choice would be 1. And then here, the meaning of 1 is, it could be 1 kilogram if you're working in SI units, or, it could be a sort of a dimensionless quantity if you kind of like decided you're going to work in dimensionless units. So it can be kind of like whatever you want. If you're interested in actually using specific units, then you should look at some of the videos that use DaVinci Newton, some of the simulation videos, where we use geometric numbers, but those geometric numbers actually allow optional units of measure, and you can do full SI units of measure. Okay, so we've got the momentum, we've got the total mass. So now let's go to our mainline function. We're going to hide the documentation from now on. And let's just set ourselves up so that the body is initially, say, at the origin. Okay, which is kind of the default anyway. And then the initial angle is going to be 0. So we're going to start in the standard configuration. And what we want to do is we want to compute the velocity. So we're going to do something like this: const v equals body dot, and then we look for what we need. P is the momentum divided by the body dot m. Okay, now I have a concern that this may not work because we haven't fully implemented the division property correctly. So let's do a little bit of testing, and if necessary, we can make some adjustments. So I'm going to print v which is body, which is just v. Okay, what do we get? So v equals 0. Let's test it out a little bit by giving the body some momentum. So let's make the body dot p equal, let's say, 1 unit in the E1 direction. So if this was SI units, the 1 unit would be a kilogram, what is it, kilogram meters per second, kilogram meters per second, mass time velocity. Okay, so I have done that, and lo and behold, my my velocity is still 0. Okay, so even though I'm dividing my body momentum, which is a vector, okay, 1e1 by a scalar. Okay, so I think we need to go and fix that. So let's just kind of do a little sanity check here, and we will also put in here print line body dot p equals body dot p, and so p is e1. That's good. And the other little bit of sanity check is, what is m? Body dot m, and that should be 1. So clearly we should have v equals e1, and we're not getting it. So we need to go to that repository, the 02b repository, or I can find it this way. So I'm looking for my Geometric Algebra first course. Okay, and what I'm going to do, in the interest of kind of quickness, I may not actually fully test this. Okay, so recall that when we did, okay, well, before we do that, we've got div here, and if I can find the usages of div, then we'll see it's the implementation of the dunder div, which is the operator overloading. So we do need to be looking at the div method, and if we look at this, you can see that the way it's doing division is it is doing a kind of ratio division. So it's kind of like saying you can you can basically derive sort of the ratio when you have like common values. So, and it becomes a scale, and the result is a scalar. So what do we want? We want the case when we divide by a scalar. So we'll have a non-zero scalar value. And what we want to do is we want to say, for example, calculate the x value. Okay, so again, I'm not really being very precise here because, or kind of completely rigorous, because I'm not implementing the full div, but I'm kind of like building it up. And we'll see in the end that maybe we'll take a more radical approach. So what should happen, it should be this dot x divided by the right-hand side dot a. Okay, so that I think should do it. And that's going to take care of the x component, but there's also going to be y. So let y equals 0. And we're going to say divided by y plus equals this dot y divided by the right hand side dot a. Okay, so this is hopefully going to give us a very sort of limited division capability, just a little bit more than what we had before. Okay, so I'll format that, and this should not break any of the existing tests. So in fact, I should be able to go here and just run my tests, and we got no failures. Okay, so I really should have a test for that. I'm not going to do that right now, just to keep the other video going. So I've uploaded that. So what I do now is I come back to my flatland, and what I need to do, if you go and look at E2GA and you go and look at div, you'll see it doesn't have the change. But if we do pull references, then it's pulled in the change. That's exactly what we want. Now we run our code, and I'll just hide the documentation, and you can see now it's calculating the body velocity is E1, which is correct. Okay, let's give ourselves a slightly different situation. Let's say 1e1 plus 2 times e2, and you can see that the momentum is that. Let's change the body's mass, so just to make sure that we're good. So the body's dot mass is equal to, and now what we'll do is we will do, say, something like 2 times geometric dot 1, which is twice what it was before, right? So if we do that, then we've doubled the mass, and now the velocity is a half e1 plus, 1e2, because 2 divided by a mass of 2 gives e2. So it looks like we're kind of good to go on our example here. So I'm just going to set the momentum back to 1e1. So this would be the body traveling to the right. Actually, let me put the mass back. Control Z. Put the mass back to 1 times e1. And yeah, what are we going to do here? So yeah, we want to move this body along. So what we need now is an update rule, like the body dot x is equal to the body dot x plus the velocity times, and we want delta t. So to get delta t, if you go to the keyboard shortcuts, there's a Greek keyboard in here somewhere, so it's like show Greek keyboard. There we go. Control Alt G. Okay, so if I hit Control Alt G, with the editor having the focus, Control Alt G, I get this Greek keyboard, and I'm going to use the delta symbol. And so what I'm going to do is I'm going to type in here const Control V delta t equals 0. I don't know, 0.1. Okay, exactly what constitutes a small time we don't really know yet. It depends on the speeds and stuff like that. So we're not going to be terribly rigorous about how we do this. Now, what we did here is we computed the velocity, and then we didn't update the position, and then you didn't really see anything happen. Okay. And my guess is the reason for that is because the update that we made was so incredibly small. If we use, say, a time of 1 unit, there you go, it's moved off to the right. But what we really want to do is we want to have this kind of animate. So the way to do that in Windows, the correct way to do it in Windows, is to ask the browser environment, which is in the window global object, ask it to tell us when the next animation frame is, and then when that happens, we call a function. So it's going to look like this. I'm going to put it down here. So I'm going to create a function called animate. This is the function I want to be called. Equals the function, some function, okay? And what I'm going to do in that function is I'm going to, well, I'll just do this bit first. I'm going to calculate the velocity of the body based upon its momentum, make an update, and then what I'm going to do is I'm going to ask the square to re-render itself so that it sees the change, okay? And, you know, we could print out the velocity. I'm not sure if this is going to be a good idea because it will probably, no, that's fine. The velocity is not going to change. I'm not even going to print it out. Okay, so here's the animate function. It's declared, but it's never read. Now what we want to do is we want to do this. We want to go window dot, and we're going to call request animation frame. And when we get an animation frame, we're going to want to call the animate function. Okay, so what will happen here, I'll just do a format to get rid of some of these linting errors. What will happen here is it will get called once, on the next frame. What we need to do now is we want it to keep on going. So that gets the first frame. What we need to do is we need to say, give us another frame, okay? So window, request animation frame, animate, and I was expecting a bit more to happen. Why are we not seeing anything? It may be because we need to do an update of the board after we've updated Bob. Yay, there we go. Okay, so a little bit of understanding how JSX graph works was required there. So it wasn't sufficient just to kind of like update Bob and move the points. We actually had to ask the board to re-render itself. And then once it did, there we go. There's our object moving off with the specified velocity. And if we change the momentum and say we point it and we give it a little bit of momentum in, say, the E2 direction, so we're kind of like going up at a little bit of an angle. There we go. Off we go. So that's the first step in kinematics. Okay, back to the theory. Okay, so that's the position. It's fairly easy to do. Let's go on to the attitude, okay? So the attitude of the body, recall, is this body dot R, and the attitude is another way in 2 dimensions of saying kind of what's the angle that the body gets rotated through from what's called its standard configuration, which is its unrotated position, to where it currently is, okay? And before we talk about this, we need to talk a little bit about angular velocity. Okay, so let's talk about angular velocity. So here's the geometric algebra way of relating the velocity of a point in the body to its position vector from the center of rotation of the body and the angular velocity bivector, which is called omega. Okay, and the formula is just that V equals R omega. So if you say it, you know, V equals R omega, it sounds exactly like formulas that you may have learned before for like circular kind of motion, except before this omega, you would normally have thought of as being either a scalar quantity, just the rate of which the angle is changing, or you may have thought about it as being a vector in a sort of a 3-dimensional example, which is sort of pointing out of the plane of rotation, okay? So this geometric algebra notation, and we'll kind of like try an example in it in a second, is really just a more general and more correct in some, well, not more general way of expressing the same thing using the vector cross product. So you might have had omega being a vector before, and then R cross omega would be a vector which is perpendicular to both R and O. It has its magnitude, which is the magnitude of R times the magnitude of omega multiplied by the sine of the angle between them, which gives you, you know, like one of these things, R perpendicular to omega. Okay, so you're going to get exactly the same thing with this. It's going to compute the same V, except you don't need to use this cross product notation, which really only works in 3D. You can use this. So let's just kind of like see that calculation in action. So supposing we're in the plane and we say that the omega bivector is the magnitude of omega, so it's like the magnitude of this guy, multiplied by E1, E2. Okay, so what we're saying is it's a bivector, it's like a unit of area multiplied by this rate of change of angle with time. It's d theta by dt, if you like it, or theta dot. Okay, so, and then I just said omega is the magnitude of omega, or it's the magnitude of the vector one. It doesn't really matter. So as an example, supposing that r is the vector which is in the direction of the E1 vector, so it's along the x-axis, and it has magnitude r. Then if we calculate v using our formula up here, v is then re1 multiplied by this. Well, the r and the omega just kind of come out the front, and you're left with e1 times e1 e2. And because it's associative, we can do the e1 times e1 multiplication before we do the e2 multiplication. And e1 times e1 is just e1 dot e1 plus e1 wedge e1, which is e1 dot e1, because e1, a vector wedged with itself is just 0, and e1 dot e1 is 1. So the e1s kind of cancel out, and you're left with just the e2. And that makes sense if you think about it. If you think about a vector which is pointing to the right, and we're rotating in the anti-clockwise sense, like this, then the velocity vector will be upwards. And if you want, try that calculation with r pointing vertically up or to the left or down. And if you work it through and you do the geometric algebra correctly, you should see that the velocity is at right angles to the radius vector. You can notice that we can also write the velocity of a point in the rotating body in terms of the reverse of the angular velocity bivector. So the reverse of the angular velocity bivector would just be omega e2 e1. We just reverse e2 and e1. And in fact, because e1 and e2 we've defined to be orthogonal, you should recall that e1 times e2 is the same thing as minus e2 times e1. And that's because e1 and e2 are orthogonal, so e1 dot e2 is 0, and so you're left with e1 e2 equals e1 wedge e2, which is antisymmetric. So this will be a useful way to represent our velocity vector in our coming proof. Okay, so we're moving along. Let's think about a rotor for our body, and we'll define it in terms of the angle through which the body, which is actually rotated, through which the body has actually rotated, which we'll call theta. Okay, so we're going to kind of construct it by constructing two unit vectors, m and n, which will give a rotation angle of theta. Well, the first thing to note is when you do a rotational angle of theta, the angle between m and n has to be 1/2 of theta. So you should remember that from the rotations video. Okay, and so all I really need to do is to set up m to be cosine theta upon 2 in the e1 direction and sine theta upon 2 in the e2 direction. So that's just basically, an arrow going up diagonally to the right that makes an angle theta over 2 to the x-axis. Okay, and we're going to set n to just be that should be n equals e1 there. Okay, let me just correct that. So no, I'll leave it, but this is n equals e1. Okay, so if you multiply m times n, if you multiply this times e1, then the e1's just, again, e1 times e1 becomes 1, and e2 times e1, you flip the e1 e2, it's minus e1 e2. So this is the formula for a rotor that will rotate us through theta degrees in the e1 e2 plane. Now you should really pay attention to the minus sign. Okay, so recall that when we do the rotation, we put the rotor on the left, the vector in the middle, or whatever we're rotating in the middle, and then we put the reverse of the rotor on the right, and we multiply all of those things through. So the important thing to remember is that, although this looks like it's rotating counterclockwise, we got to remember that there's got to be a minus sign in here. Otherwise, this is not going to work out right. Okay, so let's move on a little bit, and we'll look at the angular velocity, and then we'll kind of like we'll put all of these together. So the angular velocity bivector is just omega equals, and we're rotating in the plane, so it's just some amount of E1, E2, where omega is radians per second, radians divided by time. All right, so now to derive, we need to find r dot, because if we can find r dot, then we'll have our update equation, okay? And so what we do is, we know what r is, it's right here, so we differentiate that with respect to time. So the cosine theta becomes minus sine theta over 2, and then we multiply by the derivative of this, and you get a half theta dot, or d theta by dt. The minus sign came from the cosine differentiating, becomes a sine. And then if we look at this term and we differentiate, the sine becomes a cos, and there's no change in sine. And then we have to multiply by the derivative of that, which is a half theta dot again. Okay, so we've got a common factor of a half theta dot. And we're going to bring that common factor out to the front, because theta dot is just a scalar, so we can interchange the positions. And the other thing we're going to do is we're going to bring out E2, E1 out to the front, okay? And that's because we're trying to make this initial term look a little bit like omega, which has a product of E1, E2. Actually, there's a sign difference, but you'll see why that is. So if we bring that out, then, well, there's the half theta dot factor, there's the cosine theta, E1, E2, and we interchange E2, E1, and we get, or minus E1, E2, and we get E2, E1. So that takes care of that. And then over here, all we need to do is, to put this in as a factor, we need to have something that when we multiply it by E2, E1, it gives sort of 1. So we need to put in a factor of E1, E2, and then the E1s cancel, the E2s cancel, and we're left with a minus sine theta over 2, which is what we got there, and then you've got this leading term. So what we're doing here is just a little bit of rearrangement. Come down a little bit further, and it looks like I actually haven't didn't make a change on this line. The line looks duplicated. But what you should recognize is that this factor here, the theta dot E2, E1, is actually omega tilde, right? Because if omega is theta dot E1, E2, then omega tilde, which is the reverse, is theta dot E2, E1. And that's exactly that little bit in there. So there's the omega tilde. And then this bit, cosine theta upon 2 minus E1, E2 sine theta upon 2, well, that's just r, okay? Because we had r there before. And so what we get is that the derivative with respect to time of r is 1/2 omega tilde r, okay? Now you can think about this a little bit and kind of like go, okay, you know, is this intuitive in some kind of way? I find it hard to actually see the intuition behind this. The half factor obviously comes from this sort of doubling of the angle. Yeah, we expect the angular velocity to be in there. The rate at which the rotor changes is sort of, you'd expect to be sort of proportional to the angular velocity too. The factor of r is a little bit more, it's a little bit more sort of strange that that should be multiplied by r, but that really arises because the way that rotations combine is through multiplication. It's not through addition, right? Translations, on the other hand, you add one translation to the other. But to perform rotations, you multiply. So that's part of the, you know, I think that's kind of like the intuitive reason, at least, why the r occurs here. Some of you might like to think about this. If you've come across Euler's formula, like e to the I pi, or either e to the I theta, then that e to the I theta is just cosine theta plus I sine theta. And that formula, the Euler formula, only works because I squares to -1. Well, E1, E2 squares to -1. And so actually this whole expression can be written as the exponential of minus E1, E2 times theta over 2. because this is playing the role of I, and then this is the argument. And when you do that, saying R is an exponential, you can sort of shortcut some of this differentiate with respect to time business, because the derivative of an exponential is just another exponential, and then you multiply by this theta over 2 divided by 2, and with a factor of this, and then you'll basically get an exponential times another exponential. So that's a sort of another way of getting it, and this R then is like, that's the base exponential, and then this part is the part from differentiating the argument, which is that times that. So another sort of interpretation to think about. So we get to our update rule, and our update rule is that the final rotor position is the initial plus, and then we want r dot times di by dt times dt, or delta t in this case, because it's a finite amount, and we just substitute in our expression half omega tilde r, and that gives us the update rule for our attitude when the body has an angular velocity omega. So body dot r is equal to oh, I think I've missed out. Yeah, I've missed out the body dot r plus this. Okay, so yeah, okay, so we should do that. I'll leave it for right now again. So okay, let's look now at the problem that we have, which is similar to what we had with the position update, which is that we didn't want to use the velocity, we wanted to use the angular, we wanted to use the momentum. And similarly here, we don't want to use the angular velocity, we want to use the angular momentum, we want to store that. And the reason for that, again, is that angular momentum, or the rate of change of angular momentum, is going to connect to the torque that we apply to the body. So it's fairly arbitrary which one you use, but in some ways, I think you can think of the momenta and the momenta as being a little bit more kind of fundamental, I suppose. All right, so here I'm going to give you the preview, and then we're actually going to do the derivation. So in general, what we're going to find is that the angular momentum is connected to the angular velocity, and both of these are bivectors, through a function. Okay, this function I, where you drop in an angular velocity as a bivector, and it gives a angular velocity, angular momentum bivector out. This function here is called the inertia. In moment of inertia, inertia tensor, I mean, all of these terms kind of came before geometric algebra, and so unfortunately calling it the inertia tensor suggests something else, but it's actually kind of okay. I mean, it basically, the important thing to remember is that this moment of inertia is really generally, it's a function where you put this in and you get L out, and this can be quite complicated in 3D because the angular momentum L and the angular velocity don't have to be in the same plane. So in other words, the object may be rotating in one plane, that's its angular velocity, but its angular momentum is in a different plane. Or to put it in more sort of physicsy kind of terms, you might be applying a torque to make that body rotate, and when you do so, you're changing the angular momentum, but its angular velocity may change in a different plane. Okay, so that's really weird, you know. I mean, that takes a lot of getting used to. But we're kind of fortunate because we're actually working in 2D right now. And in 2 dimensions, there's only one plane. Okay, it's the standard E1, E2 is our oriented bivector plane. So it's a lot simpler in 2D. You can't have, angular velocity and angular momentum not being parallel. they are parallel. And because they're parallel, the moment of inertia is just a scalar. So the formula then is just that the angular momentum is the moment of inertia, which is just a scalar. This function is literally just the multiplication of omega by a number, and that's it. So it's simple. So let's just kind of like we'll do a sort of derivation of that to actually find out what I really is. Okay, and we'll do it the geometric algebra way, of course. And you'll see that we kind of get the same result that you would have gotten using using other techniques. So let's just recall a couple of things. The idea of the center of mass. This is just a definition. We just define the center of mass. It's a position. We use big X, but it's just a weighted sum of the positions of all of the points in your body multiplied by the mass of those points. Okay, so this is kind of like in the discrete representation of that. You could obviously convert this into a sum or an integral rather. Okay, and then big M is the total mass. So you should note that big X is actually what we really mean by body X. So when we have body X in our simulation, big X is actually the position of the center of mass of the body. It's not just like an arbitrary place in the body that we pick. It actually sort of means the center of mass. Okay, so when we do that, there are two alternative ways of referring to a point, or the ith point, or the point with the index I in a body. We can either use little xi, which is a vector, and I could have over arrows here, but I'm kind of trusting that by now you're kind of like getting used to not having the over arrows all of the time. So this position vector from the origin could be broken down into the vector to the center of mass from the origin, plus this little offset vector which goes from the center of mass to the point. Okay, so these are sort of two alternative ways, if you like, of referring to a particular point in the body. Okay, so let's start with the definition of the angular momentum, the angular momentum of the body, which we know it is by definition just the sum of the momenta of the individual points in the body, the mass points in the body, wedged with their position from the origin, so all the way from the origin. Okay, so this is a definition here for angular momentum. We just start with that definition. We can make a substitution for little x, big X plus Ri, and then we can just factor the two out, okay, because of the distributed law. So this is the total angular momentum, and that's just a sum of essentially two parts. One part comes from the angular momentum, which is kind of like the motion of the center of mass of the body, x, and the total momentum of the body. Okay, so we call that the orbital angular momentum because it's kind of like the angular momentum contribution that comes from the body moving around. And the second part we call the intrinsic angular momentum, which is the angular momentum that comes from the body itself spinning. Okay. All right, so let's focus on this intrinsic part because this is just a total momentum wedged with the center of mass. And you'll see it basically has this sort of form, especially I've done a conversion here, again, non-relativistic. Assume we're going at speeds which are significantly less than the speed of light. So the momentum, the linear momentum of the point, the ith mass point with mass mi, is just mi vi. Where vi, again, it's a vector. No overbars here, but it's a vector. And we say that's a good approximation because we're going slow enough. And so we can put that into our equation for our intrinsic angular momentum. Sorry for using the same symbol here when I'm just referring to the intrinsic part. But this is the intrinsic part. And now what we're going to do is we're going to, again, assume we're working in 2D. And again, this is going to provide a little bit of a simplification. And maybe in a future course, we'll work through the 3D case, which is a bit more complicated. So again, the angular velocity is omega e1, e2. And because we're working in the plane, the offset of a given mass particle, mass point, from the center of mass, big X, is just xi times e1 plus yi times e2. Okay, it's just a vector in the plane. Okay, and as we said, for a rigid body in 2D, we can write that the velocity is Ri times omega. Okay, so immediately we can plug this into this formula here, and we get that the intrinsic angular momentum is that. Okay, and notice the wedge is happening with all of this. And then we can substitute in our Ri and our omega. So here's Ri coming in here, and here's the omega. Okay, and we first can multiply this together. We can do that. So we do that, and we get this vector here. So let me show you how that works. It was xi e1 times omega e1 e2. The e1s cancel, if you like, to give 1 again. We've met that so many times, I'm going to assume you're familiar with that. So we're left with xi times omega, there's the omega on the right, and then the e2 stays. So we got xi e2. Now this yi contribution is a bit more complicated because it's hard to multiply that together, but if you realize we can exchange these two, e2, e1, and put a minus sign there instead, and then the e2s will cancel, so we'll get a minus sign, the yi, the e1 now, because that's what's left over when the e2s have canceled, and we get omega. Okay. All right, so now, because we've got a vector here, we've got a vector over here, it's pretty easy for us to compute the wedge product. So let's compute that, and only a few terms get left. Okay, so if you use the distributive laws, you can use your old FOIL trick, first, outers, inners, last. So the firsts are xi e1 wedged with xi e2, so that's xi squared e1 wedged with e2. And then the outers, xi e1 wedged with yi e1. Well, e1 wedged with e1 is 0, so we can forget about that. And then similarly, we can forget about the inside terms because that's e2 wedged e2. And then we've got the last terms, which is yi squared. There's a minus sign, and then there's an e2 wedge e1. So there's minus yi squared e2 wedge e1, and then there's the omega, of course. And now I hope you'll start to recognize that e2 wedge e1 is just the same as minus e1 wedge e2 because that's anti-symmetric. So we can flip the order of those guys and then factor that out as well. So we've got omega e1 wedge e2 xi squared plus yi squared. And this omega e1 wedge e2 is just omega because e1 wedge e2 is actually the same as e1 times e2 because e1 is orthogonal to e2. e1 dot e2 equals 0. So we can put omega here. And now what you see, or some of you might have come across this formula already for what we call the moment of inertia, okay, in 2D. So the moment of inertia is this number that we can kind of calculate for a body, and it's a scalar quantity, just because mass is a scalar, and these are just magnitudes. So here we go, scalar quantity, and it's multiplied by omega. So as I promised before, in 2 dimensions, the angular momentum is connected to the angular velocity just through a scalar. It's very simple. This is not a function, okay? Or rather, it's a function that just multiplies. And obviously, because this is a scalar, we can invert it. So if we want to calculate the angular velocity and we have the angular momentum, we can just divide the angular momentum by the moment of inertia, and that gets us our omega. And so here we've got the conversion. We compute the angular velocity from the body's angular momentum divided by its moment of inertia. And then here's the update of the body. And this one is actually correct. I can see we've got body.r equals the original body.r. And then what we need is the r dot expression dr dt multiplied by dt. So it's r plus dr, if you like, or r plus delta r. So since r dot was computed it to be 1/2 the reverse of omega times r, that's where all that comes from. Okay, and the only thing here is, you might observe you can use the reverse method, or in our operator overloading that there's a unary and we use a little tilde sign just before the omega. That will work as well. Okay, so that's the theory. It's a little bit long and involved, but a lot of it, it's really great practice at using geometric algebra in 2D. And to be quite honest, in 2D, I don't think it really gets any more kind of complicated than this. So yeah, take your time to go and look at that, play with that, maybe make sure that you can reproduce it yourself is probably a good idea. If you find I've missed a few things here because this is a bit more of a conversion course than a fundamentals in sort of classical mechanics. So you may need to kind of like go and sort of refresh yourself on things like center of mass, but obviously try and translate it into geometric algebra speak. Okay, let's get to the coding. So I'm going to bring back the code. So now we're ready to do the final step in our animation, which is to change the attitude of the body in response to a change in its in response to the fact that it has an angular velocity. So we need to add to the body the angular momentum property. We also need to add to the body the moment of inertia property, and then we'll do a division to get the angular velocity. Okay, let's do that. And then this update has to happen in the animation loop. All right, so let's go back to our rigid body, and we want to add, in the same way that we sort of added these properties to make the particle move, or rather the rigid body move along, what we want to do now is we want to add angular momentum to keep track of the angular momentum of this rigid body, and that is going to have the symbol L. And then we want to have the moment of inertia, and that is going to be, we'll give it the symbol I. Okay, not to be confused with the fact that we sometimes use I to represent what we call the pseudoscalar of the space, which is E1, E2. Often happens that we use the same symbols, can't be helped, but this is a good symbol to use for the moment of inertia. So we've got the angular momentum, got the moment of inertia. So let's go back to our main line and just check our new properties. Let's just see what we've got first in terms of running its moving off. We'll set the momentum back to 0 to its default value, and that will just leave our square in the starting position. Okay, so we want to take a look at the angular momentum, see what that is. And the angular momentum is currently 0, and we want to look at the moment of inertia, and that is 1. Let us give our body some angular momentum. So body.L equals, and angular momentum, recall, is just a bivector. So, any old value will do here. I'll just use E1, E2. And so we can see body.L is E1 wedge E2. The moment of inertia is 1, and we should be able to do division of our angular momentum by the moment of inertia. So, and I'm obviously doing this because I suspect that we haven't implemented it in our geometric algebra. So there we go. If you divide the angular momentum by moment of inertia, which is 1. We're currently getting 0, and that should just be U1 by G2. So let's go back to our Geometric Algebra first course. And we were just looking at this, so we're going to look at division. Yep, we're not really doing anything with the bivector part, so I'm going to create that. And what we want to do is implement division by a scalar. So here's where the right-hand side is a scalar. So we'll get B, just like these others, is B, this dot B, and divided by the right-hand side dot A. So if you look at this whole method right now, you can see it's really working in two modes. One is you can do division by a scalar. That's what this whole block is doing. And then in general, we've also got sort of the ratio kind of division. So a vector can be divided by another vector which is in the same direction, or a bivector can be divided by a bivector. So again, it's a very limited division, but it will work for us. I'm just running the tests here, and although I haven't written any extra tests for this, and I should, I haven't broken anything either, so that's good. Okay, I'm going to upload this, and that means that we will be able to come back to Flatland, and here's our geometric algebra number. There's div, and if I pull references from the project menu, you can see we've got the extra bit of code in there. So now if I run, hide the documentation, take a look at the angular momentum, it looks like we're getting the correct division. So just to prove it, I'm going to set my body dot moment of inertia to be, say, 2 times geometric dot 1. So twice as much moment of inertia, and I get a velocity which is 1/2 E1 by G2. So good, so far so good. So now what we need to do is we need to this time perform an update of our rotor. So recall the formula for that is going to be body.r equals the old body.r, looks kind of similar, plus, and then this part is what we call r dot, the rate of change of r, and then we multiply it by this same delta t here. So what we need to do in this whole thing is we need to put in our factor of 1/2 multiplied by our omega. So I'm going to go Control-Alt-G, go to the Greek keyboard, and get omega, and drop omega in there, which, whoops, Control-V, omega, which needs to be reversed. And it doesn't know what omega is at this point in time. That's why it's kind of complaining. And then we need to multiply also by body.r. So that's our full formula for our update. We need to calculate the angular velocity. So const omega equals body.l divided by the body.moment of inertia. And hey, look at that. We've got it. We've got some rotation going on here. I think the ABCD thing is getting a little bit old. Let's get rid of that in the square. So go back to the square, create point. I think I'm going to go with label false. With label false. Does that do it? Yep, it's going to do it. So we'll order 3 more of those. And we've gotten rid of that. A little bit of formatting. So our body is rotating fairly slowly. If we gave it more angular momentum, then it would have greater angular velocity. So there, it's going a little faster. Let's kind of like take it up to 5. Yeah, going pretty fast. Maybe 10's a bit. 10's still manageable. If we go in the opposite direction, put a minus sign in there, we're off in the other direction. So everything seems good. So there you have it. We have managed to connect our position and attitude variables in our rigid body, and we've been able to change them by setting linear momenta and angular momenta, and we had to go through the step of converting both of those into linear velocity and angular velocity. I hope you enjoyed the video. We are in a great place now to add the dynamics of our simulation, which is where we just choose a force or a torque, and we can apply that to our simulation. Okay, I hope you enjoyed it. If you did, please hit the like button. It just lets me know that I'm on track. And if you want to see more videos like this, hit the subscribe button below. More will come your way. Until next time, take care and happy coding. Goodbye now.